Hello again to SanfordFlipMath. This is PreCalculus. We are going to be doing 1.2b, which continues our describing functions. Just a speedy recap. Remember that the point is to develop a vocabulary, a working language, to start talking about functions, their attributes, equations, etc. We've already talked about domain, the allowed x values, the range, which is the possible y values or output values, and asymptotes, which are closely related to domain and range, but again not completely the same, and they are lines, or it would be a line that the graph approaches, but gets closer and closer and closer to, but in that area of the graph it's never going to actually get there. It continues to get closer, but doesn't actually get there. Related to vertical asymptotes are also discontinuities. Discontinuities, today we're going to add on discontinuities, increasing and decreasing, and extremes, sometimes called extrema, plural for extreme. Okay, so discontinuities, abbreviated DISC. Discontinuity is a break in the graph. In other words, if you were trying to draw the graph going from left to right, I'm going to try and draw the entire graph, like one of the examples we saw last time. It looked, I don't know, it wasn't exactly like this, but it was something like this. And the idea is if you try to trace over this graph going from here, and then, well, you have to pick up your pen or pencil to continue. Okay, so that's the idea. So there's this big old break in the graph, and that is a discontinuity. Well, there are actually three different types of discontinuities. The one we just saw there is called an infinite discontinuity. When usually it's associated with a vertical asymptote. It is possible to have an infinite discontinuity when you have like a hunk of graph over here and a hunk of graph over here, and in the middle there's this abyss, there's this big black hole, and so that is also infinite. There's also breaks in the graph where they're called point discontinuities, and that's when you have like a single point missing. So this is a point discontinuity, and sometimes that's called a removable discontinuity because you can just add a single point and the discontinuity then is removed. Okay, and then lastly, the third kind that we will deal with is a jump discontinuity, and this kind of like when it looks something like that. Or maybe if you've seen the greatest integer function, a step function, it kind of looks like this. Oh, that's supposed to be open, sorry. And so every time you're coming along from chunk to chunk, you come along and then you got to jump, and then you come along and you got to jump, and you come along and you got to jump, etc. You come along and you got to jump, and they don't always have to be going up. You can have something that looks like this, and then it picks up over here. And so again, the idea is we got to jump down to get there. So that's jump discontinuity. So three types of discontinuity: infinite, usually it's an asymptote, vertical; point discontinuity; and jump discontinuity. Worth noting that when you have a horizontal asymptote, that is not considered a discontinuity because we're not talking about a break in the horizontal direction in the x and y direction. Also should note that when you state a discontinuity, typically you state the type, so infinite, point, or jump, and where it is located, so its x value. So for instance, if this point was at 2, 1 in this middle graph here, then we would have a point discontinuity at x equals 2. Okay, don't list the whole point, just list the x value. For this one, maybe we have an infinite discontinuity at x equals -1, or something like that. Okay. If the equation does not have any discontinuity, then it is just referred to as continuous. And where is it continuous? It's continuous everywhere. Sometimes you'll be asked this entire question backwards. Where is the function continuous? And it might be everywhere except at x equals -1, or except at x equals 2. Or something like that. Or you might even say over its whole domain if the domain is listed already. Okay. All right, increasing and decreasing has to do with whether something's going up or going down. And in English, in our culture, typically we read from left to right. So if we list time on a graph, if we show things on a graph for the x direction, it generally increases to the right. Well, so if a function is increasing, that means it's going up as we go from left to right. Think of it like positive slope. So increasing is like positive slope. Okay, and so, yep, there it is. Okay, so this would be increasing. This would be decreasing. Doesn't have to be straight. Could be decreasing like that. Okay, and the interval where that happens is where this occurs. So, for instance, you might actually have, let's say we have a cubic function. Okay, so third power function. And let's say this point's at -1, 1. And let's say this point is at 2, -1. Okay, so this graph is going up as I go from left to right there and also there. So the parts of this graph right now that are in red are increasing. Okay, so I could say this graph is increasing, well, to the left of -1, which you could write x less than -1, and to the right of x equals 2, so x greater than 2. Now again, you could write both of these in interval notation. So you could say -1 comma, -infinity comma -1. So -infinity, -1. Or it's also increasing to the right of 2, so from 2 to positive infinity. Now, probably worth noting, it's not actually increasing at at -1 or at 2, because at those places the slope would actually be 0. It's not going up or down. Okay? All right, this spot in the middle for this particular graph happens to be decreasing. So it's going down, its slope is negative. So this is decreasing between -1 and 2. So this is the spot where interval notation is like the bomb. You could write -1 less than x less than 2 also. Okay? And lastly, for our list of vocab, is we're going to talk about extremes, maximums, and minimums. This is kind of obvious, but I have to make a big stink out of little details. Okay? An extreme, or maximum or minimum, is the y value. Okay, so it is a high point or a low point on the graph. The y value itself is the max or the min, and its location is the x value. So when we think of locations in math, it's x values. But the values of the function are the y values. Okay, so just a quick little conceptual example. Okay, so this point right here, let's just say it has an ordered pair of 0, 2. Okay, it is a relative or local maximum of 2, and its location is at x equals 0. Don't just write 0, 2, because then that masks the issue of, do you understand that the maximum is actually 2? Okay, now it's a relative maximum because there's this spot over here to the right where this function is actually higher than the maximum. Okay, so it's a maximum compared to the points it's near, but not compared to these guys over here. Okay. Similarly, if this point, let's say it's 3, -1, okay, this would be a local, or again, you can call it a relative, local or relative, not your relatives that live nearby, but local or relative, and you don't have to write them both, minimum of -1, and it is located at x equals 3. Okay. Typically, you'll see parabolas all the time. So let's say this point is -2, 3. This would be an absolute max of 3 or equals 3 at x equals -2. Okay. No minimums, no local, no relative. Okay. All right. Let's do another example. Okay, so I'm going to call this example 1 because it really has an equation and all that kind of stuff. So square root of x minus 3 plus 1. Okay, and I want to make sure that we hit the ideas that we're talking about right now. So we're talking about max and mins, we're talking about, that is extremes, we're talking about increasing and decreasing, and we're talking about discontinuities. Sorry, it's just the order I remembered them in. Okay, all right, so this is symbolic. This is a symbolic representation. This is what this equation is about. And you can kind of, think about, remember that you can't take the square root of a negative. So you know that in terms of domain, didn't ask you about domain for this right now, but wouldn't the domain have to start at x equals 3, where 3 minus 3 is 0? You can't take, if x was 2, then 2 minus 3 would be less than 0. You can't take the square root of that without making a mess. So the domain is actually x greater than or equal to 3. Also, when you take a square root, the answer to that's always positive unless the inside is actually 0. So that means that the smallest value for this would be 0 plus 1. So the range is actually going to be greater than or equal to 1. Now I know some of you looking at that and going, what the heck just happened? All right, so let's just do a speedy little table here. Again, I know 3, 4, 7. I picked 3 because it makes the inside 0, and square root of 0 plus 1 is 1. I picked 4 because I know 4 minus 3 is 1, and the square root of 1 is nice. Plus 1 is 2. And I also picked 7, so I'm picking these a little strategically. You don't have to do that. 7 minus 3 is 4, square root of 4 is 2. This is 3. Okay, so I'm plotting some points here just so we kind of get an idea of what's going on. So 3, 1, 4, 2, and 5, 6, 7, 3. Okay, now be careful. You've been connecting things all your life in algebra. But just a quick little reminder, if I put 2 in here, 2 minus 3 plus 1. The square root of negative 1 plus 1, sorry, that's imaginary. And we're not really doing that right now. So 2 is out. So do not connect anything to the left of this thing, or you're going to be, kind of mad at yourself. Okay, so nothing there. Okay, just note to self, nothing there. Okay, I don't want to really erase. I just want to, let's back up. Whoop. There we go. Okay, so domain, the y, x values rather, greater than or equal to 3. The range above there, greater than or equal to 1. Okay, so just to remind you. Are there any breaks in this graph? Where, as I'm tracing along this graph from left to right, is there a spot where I'm drawing the graph and then I have to stop, pick up my marker, pencil, whatever, and then continue graphing? There really aren't any. Okay, so there are no discontinuities. So I'm just going to say this is continuous. Okay, it's looking good. Okay, increasing, if you recall, is where is this thing going up? Well, it looks like it's going up this way. And now this doesn't go horizontal, like an asymptote. It just gets horizontaler. I know that's not a word. It communicates though. It does appear to get flatter. But so it's increasing in all of these points. So where do those points begin? Well, looks like to the right of 3. So this is actually increasing for all of the x values greater than or equal to 3. Well, where is it decreasing? It's not. Remember, you don't do increasing and decreasing from right to left, like as in reading Hebrew or Arabic. We're reading in English, and graphs are numbered from left to right. Again, think slope. Positive slopes go up, so that's increasing. Negative slopes go down, that's decreasing. Okay, again, from left to right. Okay, maximums or minimums. Okay, well, out here, this is going to keep going up. Even though it's going to go up more slowly, it's still going to keep going up. The only real spot where there's a maximum or minimum is this little guy right here. There is a minimum there. Minimum is the y value. And what y value is that there? Well, that appears to be 1. So the minimum is y equals 1. It is located at x equals 3. The only other question is it absolute or relative? Absolute or local? Is this the lowest spot on the entire graph. And if that answer is yes, it's the lowest, then this is an absolute minimum. Okay, so it's an absolute minimum of y equals 1, and its location is at x equals -3. That's it. All right, well, we're going to get one more in here, and this one will be, as I like to say, interesting, which you can translate into hard. Stuck that in, didn't I? Okay, so x plus 1 over x squared minus 2x minus 3. Okay, now again, we are talking about discontinuities. We have to state what type they are and where they're located if there are any. We're also talking about increasing, decreasing, and we are also talking about any extremes, extrema, maximums or minimums, maxima or minima. Yes, those are words, believe it or not. Okay, might be worth talking about domain, range, and the asymptotes. And keep in mind what we're doing is we're building a list, and ultimately we're going to be doing all of these things all at once. Okay, we're focusing on one, chunks at a time. But all right, quick note: domain is about x values, what x values are allowed, and as soon as you see a fraction, you need to be saying to yourself, the denominator cannot equal 0. So x squared minus 2x minus 3, when is that equal to 0? Now, if it's me, and it is, I'm going to factor that bad boy. Sorry, I again used the F word. X times x is x squared. This is negative, so that means these had to be different. I know that factors of 3 are only either 3 and 1 or 1 and 3. I'm going to stick 1 and 3 in there, and I need to check outer and inner to make sure this really worked, and I'll combine those. I'm thinking of the FOIL acronym. So 1x plus -3x is -2x, and that worked. Okay, so I'm going to rewrite this whole thing as, okay, so that's the original equation. So what values make the denominator 0? Well, x equals -1 would make that 0. X equals 3 would make that 0. So I'm going to put that in my little domain spot. X can be anything in the universe, just not -1 and not 3. All of the x values need to be both of those things at the same time. And I know we've been using that word or a lot lately, but in this case, it's really and. So the x values that work have to both not be equal to -1 and also not equal to 3. Okay. All right. Now, I mentioned a big stink about these two being connected to each other. Domain and vertical asymptotes are connected to each other. Well, there's a little bit of an issue, though. If I look at the graph of this thing, and I should have opened this up before, if I look at the graph of this thing, we're not going to see two vertical asymptotes for this. So, come on, it's loading. We're almost there. All right, so, oh, come on. There we go. Cool. All right, now I got to remember what the equation was. All right, so y equals, I believe in the numerator it was x plus 1. Okay, divided by, in the denominator, again, x squared minus 2x minus 3. I'm hoping that's right. Okay, and I'm going to go to Zoom 6 just to see what happens. Oh, that's nice. All right, this is for you, big screen version. I only see one asymptote. Okay, now I want to take you back to the equation, and I know some of you are already ahead of me, and I appreciate that. Look at this. Can't we just then, bam, goodbye? Wouldn't this, now be careful, that x minus 3 is still on the bottom. Wouldn't that be it? So wouldn't the vertical asymptote really just be x equals 3? Which begs the question, what about the domain? If you can cancel that out, doesn't the domain only end up being x not equal to 3? And quick note here, domain must be from, nice English there, the original. In other words, not simplified. Because it still would have made it 0 over 0, not just dividing by 0. And if I go back to the equation here, I'm sorry, the calculator here, let's look at this. Notice that -1 still shows an error, and 3 also shows an error. So that's saying the calculator says, look, I can't even use -1 or 3. Okay, so quick note to self. Okay, so this is one of those spots where, yes, they are connected, but they are not identical. Okay, there are discontinuities, however, on both of these. So x equals 3 is infinite discontinuity, and x equals -1 is, well, what? All right, well, let's pop back over here, and let me go back to the graph, and let me get rid of this if I can do my little trick. Nice. Okay, I'm going to cheat a little bit. I'm going to do zoom 4. Zoom 4 is actually zoom decimal, and the cool thing about it is it actually shows you things like this, because when you hit trace, it actually counts by tenths, and so you can see it kind of, notice the x values are going by tenths now, so that means that when it graphed here, it actually graphed exactly -1, whereas the other screen didn't. And if I come back over here, come on, whoop, 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 whoop. One more. Oh yeah, look at that y value. Yeah, you're saying to yourself, what y value? That's what I'm hoping you're saying. There is no y value at that point. Okay, so if I was going to draw this by hand, okay, and I know the graph's right here, but you need to know how to get this on paper. Okay, so here's the right chunk of this, and here's the left chunk of this, but right there, oh, that was nice. Sorry to erase too much. Right there, there needs to be a hole. So what I'm illustrating here is that if you're drawing this by hand, you would draw a little open circle there to show that that point's missing. There's your point discontinuity, sometimes lovingly referred to as a hole. Okay? All right, range, a little more complicated this time. Horizontal asymptote, a little more complicated, well, a little bit more. I don't think I mentioned to you last time. I'm going to give you a sneaky way to get the horizontal asymptote, and I may have mentioned it in class by now. But notice how this is x squared. If I match that up, this is the highest degree of x in the whole equation. If I match that up with the x squared in the numerator, okay, yep, I don't see one either, so there must be a 0x squared in the numerator. 0x squared over 1x squared, okay, and this is to find the horizontal asymptote. 0x squared over 1x squared is, you guessed it, 0. That's the horizontal asymptote. Now, again, as we mentioned before, that is closely related to range. Well, if you pop back over to the graph, if you notice, okay, I don't need any of this. If you notice, this is getting closer and closer to the x-axis, but it's actually never going to touch. Same over here. Okay, so y equals 0 is not in the range. So y does not equal 0. But there's one other little issue here, and this is the tricky part. It's this. There's no point there. I know you're saying, what's your point? Thank you. So at x equals -1, there was a discontinuity, a point discontinuity. Well, that point actually has a y value too, or doesn't have a y value. And if I go slightly to the left of it, -0.24, go slightly to the right of it, -0.25, what do you think? I mean, now, here's the issue. You can't really calculate because it makes it 0. It makes it 0 over, well, that was nice, actually. It makes this thing 0 over 0, and that's a problem. But you can put it into the simplified version, and if I put a -1 in right there, this becomes 1 over -1 minus 3, also known as 1 over -4. So, -1/4. That is the other part of this ordered pair that isn't here. Okay, and that's what we're trying to do, is describe the function. So, and, because y has to be not equal to 0 and not equal to -1/4. And if you want to write that as a decimal, I don't really care. That's fine. Okay? All right, let's pop back over here. The rest of this is going to go quickly. Okay, that was interesting. Where is this increasing? Okay, it's probably worth noting, I probably say that all the time, sorry, that this is all decreasing except there. This is all decreasing. So this thing looks like it's really decreasing everywhere, except the places it doesn't exist. So it's not increasing anywhere. It's decreasing from, you could say, from negative infinity to negative 1, or from negative 1 to 3, or from 3 to infinity. Okay, you could say it's decreasing everywhere except, or, well, you don't even have to write the word except. You could say all real numbers where x is not equal to negative 1 and not equal to 3. Oh yeah, that's nice and easy to read. Sorry. You can rewind if you need to see that back there again. Okay. All right, so again, it's decreasing everywhere on its domain. Okay, one last thing. Any maximums or minimums on this bad boy? Any spot where it goes up and comes back down like that, or it goes down and comes back up, or maybe goes up and stops? This is not a max or a min because it's decreasing to get to here and it comes right out of it decreasing again. This is obviously not a max or a min because there's nothing even connecting it there. So this is decreasing here, still decreasing. It has to go from decreasing to increasing or increasing to decreasing to be considered a max or a minimum. So that's it. There are no maximums, no max or min. Okay? All right, more in class. It's been fun. Bye.